This video is going to cover section 2.5 and it's going to discuss infinite sets. Okay, so this entire unit is actually largely based on the findings of someone called George Cantor. Okay, we're not going to talk too much about him, but if you want to do a little bit of research, he's definitely a mathematician that would be interesting to read about. Okay, so we're going to go ahead and start right away with a definition that's going to lead us to this infinite set. We have it a one-to-one correspondence, okay, between two sets A and B is a rule or procedure that pairs each element of A with exactly one element of B. So we have kind of seen this in class, maybe in Algebra 2 or so, where you talk about the domain and the range and that a function can only be a function if there's only the x's don't repeat, okay? And so part of that has to do with this one-to-one correspondence. In other words, for every x, there's exactly one y. And it works the same way with sets. So for example, and I'm just going to kind of jump into these because these are not too bad. By the way, this video shouldn't be too long, so hopefully that's some good news. Let's say we have a set A is equal to 1, 2, 3, okay? And set B is equal to 7, 8, 9. Okay, so what I can do with this is I can kind of set these up to where I can match one of the A's. I can match one of these, match one with one of these, with one of these elements. Okay, so we're gonna kind of do that. Let me show you how I would do this. I would probably line up. I would start with A. So 1, 2, 3. And I'm gonna just line it up on top of B. So I'm gonna take B and put it right underneath, okay? And I'm just gonna draw some arrows from one to the other. So I can do it like this. 1 goes to 7, 2 goes to 8, 3 goes to 9. And this shows that we have a one-to-one correspondence, okay? Similarly, I can go ahead and do this a different way. I can rearrange the elements because they don't have to go in that order. And I can do 3, 1, 2, and match it to, let me see, let me change this up a bit. Let's just go backwards. So 9, 8, 7. And it still works. So I can match up the 3 with the 9, the 1 with the 8, and the 2 with the 7. So there's multiple ways that I can do this. And that's actually one of the questions you're going to have is, I think, for one of your homework problems, is how many arrangements could you have? So you just have to kind of list them. But this shows that we do have a one-to-one correspondence. Okay, this is just two ways I could show it with this particular example. So every element in A matches up with an element in B exactly once, and vice versa. Which leads us to a note here at the bottom. It says that two sets A and B are equivalent, but we've seen this before, if and only if A and B can be placed in a one-to-one correspondence. So if we have this one-to-one correspondence, like we showed two different ways here, then that means that the sets are equivalent. Remember that equivalent means the same number of elements, and we saw that in a previous lesson. Okay, so if you can show that something is one-to-one, like we just did, then that proves that they're also equivalent, the two sets. Okay, so I'm going to go ahead and jump down to this example. Like I said, this is kind of a not too long of a video. Establish that the following have a one-to-one correspondence. Okay, so we're going to go ahead and do what we did right now. And remember that if it does have a one-to-one correspondence, that means that A is equivalent to B, meaning the sets that have the same number of elements. Okay, so let's see. We have for letter A, the set of natural numbers and the set of integers. So we have to remind ourselves what that is. The set of natural numbers, that's this one, okay, is this fancy n, and it starts with 1, 2, 3, 4, and it goes on and on, okay, all the way up to forever. Okay, the set of integers, on the other hand, is represented in our book by an I. So this one is represented by an I, and this one kind of goes. It starts with the negative numbers, but it starts with those dots where you have -3, -2, -1, 0, 1, 2, 3, and so forth. Okay. So this one is a little bit tricky because I believe most people would say, oh, well, the integers have more numbers than the natural numbers because, the natural numbers don't have the negative ones and they don't have zero. But believe it or not, these do have a one-to-one correspondence. I forgot this quickly here. Okay, so I'm going to show you that. And the way I'm going to do this, I'm going to go ahead and line them up a certain way. So the naturals are going to stay how they were: 1, 2, 3, 4, and on and on and on. Okay. And at some point, we get to 2n minus 1. Now I'll explain this in a bit. 2n, and then it keeps on going. Okay. So just before, I know that this part probably confused you. 2n, we'll put a note right here. 2n is going to be all of our even numbers. Like, so in other words, at some point we get to some even number. Okay. Which means if I subtract 1, so if I take away 1 from whatever number this is, would be 2n minus 1, and that would give us the odd number right before it. So because the natural numbers go on forever, this is just a general statement saying, well, at some point we have this even number, and at some point we have an odd number, okay? And of course, it goes on forever after that. So just keep that in mind, okay? And then we're going to go ahead and line up the integers underneath it. So the integers are going to go underneath. But what I'm going to do, instead of writing it like this, I'm going to rearrange it, and I'm actually going to start with 0 because I don't want to have dots. I don't have dots on this side of the natural number, so I can't have dots on this side. They do have to line up one by one. So I'm going to start with 0, and then 1, and then -1, because I want to include both positive and negative, okay? And then 2, and then -2, and so forth, okay? And at some point, we're going to get to some number n, okay, just like we kind of have the 2n over here. And n is just a number. So again, here I'm just going to put n is just some number in the integers. So it's a number in the integers, okay? And so one number before that would be -n plus 1. Now that might be a little confusing too, because you're saying, well, it would just be n minus 1. But look at the pattern that we have here, okay? We have one positive, one negative, one positive, one negative. So this just kind of takes care of that for us. Okay. If this part confused you, that's okay. You could also do n and then just add 1 to the next one to move on to the next number. Okay. But anyway, so now we have a similar pattern. Okay. We have, we can match up this number and this number. We can match up this one and this one, 3 and -1, 4 and 2, and then next we would have 5 here. So 5 and -2, dot, dot, dot. These two match, and these two match. And it goes on forever. So we have in fact proved that the set of natural numbers and the set of integers have a one-to-one correspondence, which means that they're also equivalent. Okay? This is actually one of the more difficult problems. So if you didn't understand it completely, that's okay. Let's try to do the next one. Okay, remember we can always discuss this further in tutoring. So I'm going to jump down to letter B and scroll down so we can have a better view of that. This is kind of like the first one where we're just going to match these up. So we have set A is R, E, F, and H. Okay, and then we have set B, which is going to be our 4, 5, 9, and 10. And I'm going to see if I can match these up in a one-to-one correspondence. So let's see. I can match my R with the 4, my E with the 5, my F with 9, and my H with 10. So I mentioned earlier domain and range. If it helps, because I know that you're more familiar with that, you can think of this one kind of like as a domain and this one kind of as a range. Just to help you, it's not that, but it's not actually domain and range, but the idea is we want to match one to one element from A to one element in B. If we can do that, then that proves that these two are one to one and therefore also equivalent. So we can say, yep, oh, wrong one. We can say, yes, this is equivalent. So therefore I'm sorry, one to one. So therefore A is equivalent to B. Okay. And the last one, letter C, the set of real numbers and the set G, 0, 1, and 2. So this one's a little bit tricky because the real numbers, we haven't talked too much about those, but the real numbers are every single number in pretty much the main set of numbers that we use. So it includes, it's going to be kind of hard to do this one. Okay. It includes everything. So I'm going to say X belongs to the real numbers. So here on the side, let's make a note here. This includes all numbers we can think of in the real plane. Okay. So in other words, it's infinite. And there's that infinite where we're going to be seeing later. So this one is infinite and G is just 0, 1, and 2. How are we going to match up 3 elements with infinite elements? We can't. So this one does not have a one-to-one correspondence. You can only match up an infinite set with another infinite set, okay? Which is going to bring us to our next little topic here. A set is an infinite set if it can be placed in a one-to-one correspondence with a proper subset of itself. So this kind of goes into what I just told you. If we have a set of numbers that is um, infinite, okay, we can take out subsets of it. Yes? And we can keep doing that over and over and over. So just to really quickly remember that a proper subset is a set whose elements are in its superior but not equal to. In other words, we can take out let's say we have the set of natural numbers. So 1, 2, 3, and on. Okay. A proper subset of this, I could just take out, let's say, the first 3 elements. 1, 2, 3. And this would be considered a proper subset because 1, 2, and 3 are all inside here. There's 1, there's 2, there's 3. But this is definitely not equal to n because, well, n has a whole bunch of numbers. This one just has 3 elements. Okay? So we're going to verify if the following are, in fact, infinite sets. You know, guys, I might have to cut this video. I'm having some technical issues. So we'll have a part 2 in just a bit.